I will try to explain step by step how to detect a fault in an adapter, how to repair it, and what you need to pay attention to. And this video might be a bit long. The goal is to reach a conclusion. I hope we will achieve the result. This adapter is a very special one belonging to a Vestel brand DK rechargeable vacuum cleaner. Before disassembling the adapter, we need to perform some external tests. We look at the values on it and check the diagram here. As you know, standard adapters consist of plus and minus. Here, apart from the plus and minus, there is also a separate terminal. So, there are 3 paths running inside this cable. There is a plus, a minus, and one COM-MS, meaning a serial communication line. When measuring the socket, measuring from the pin can be misleading, meaning you might think it's broken. The middle pin is the COM-MS path, so no voltage will come from there. We cannot measure this adapter as we do with standard adapters. Measurement is quite easy in standard adapters. When we touch the minus and plus to the tip, it will give us the measurement. If you're measuring a 3-way charger, you must be very careful here. The pin here can mislead you. When you hold the negative to the outside, there is a metal part inside the socket for the positive. It becomes clear when I touch it like this. You need to measure from the metal part. When I measure it now, we unfortunately see that no voltage is coming through. We can do one more check here. Let's unplug our adapter. The reason for no voltage might also be a break in the cable, meaning the negative or positive path might be broken. To verify this way, we set our multimeter to resistance mode. We hold our negative probe on the outside. With our positive probe, we first check the COM-MS path, meaning we touch the pin. We read a resistance value. As we said, there is also a positive path inside the socket. We look at the positive path as we read a resistance value from there too. In this case, we have tested our cable. In such adapters, you can also measure cable continuity in resistance mode. Now, let's open our adapter and start fault detection. Disassembling these adapters is a very difficult and strenuous task. Definitely do not force it with a cutting tool or anything to disassemble the adapter. Because these adapters are made using a compression method, you must use chemicals. I will use a spray here. You can also open it with gasoline. There are videos on my channel on how to open adapters. I will also leave those videos in the description section. By watching those videos, you can easily open such an adapter. When we examine our adapter, there are absolutely no screws or anything on it. We apply some spray to the edges. We wait a little while. A little later, the adapter will open by itself. As you can see, it started to open. Definitely do not try to open it without using spray or gasoline, or it will be very difficult. It came out by itself. It was glued from the inside with silicone. I want to make an important warning here. When we look at our adapter, there is a 400 minus volt capacitor. You must definitely short circuit this nice capacitor or discharge it with a bulb like this. Because we just plugged it into electricity and the capacitor here might be charged. We touch the positive and negative of our capacitor. It's done. I already explained it just now. There are 3 cables. There's plus, minus, and white one. Here, this is also a data cable. I can say it is the cable that provides communication with the battery BMS circuit on the vacuum cleaner. Now that we have disassembled our adapter, we can measure our cable from here too. We set our multimeter to short circuit mode. We check the negative path. The data path in the middle section. That is also working. We attach our probe to the inside of the connector tip. This is our positive path, meaning the red path. We have also verified the integrity of the cables from here. We measure from the outside. There is no voltage coming through. After discharging the capacitor, we visually inspect all components on the board. Below the board. Is there any burnt or exploded component? When we look like this, it is visible. No failures apparent. It consists of 2 sections. The part separated by the optocoupler here. This is the DC side, and this is the AC side. We start measuring from the fuse first. Our fuse is intact. There is a non-polarized capacitor. We are checking that. Right here, there is an NTC. The NTC should not be an open circuit. Our NTC is intact. We have a varistor. The varistor should not be short-circuited. There are also 4 resistors. We are checking if these are short-circuited as well. We especially need to measure the bridge rectifier. Let's measure it in short-circuit mode first. There is no short circuit. Let's measure it in diode mode. As of now, no faulty parts have appeared up to the bridge rectifier. This is a good sign. If you are working on this type of adapter and the capacitor charges every time you plug it in, a fault in this input stage is unlikely. Let's look at the diode side of the optocoupler. Let's also measure the optocoupler in short circuit mode. Our optocoupler is intact. There are numerous resistors on the 220V side. We are looking at these one by one as well. Some resistors may show a short circuit because they have low ohms. Just like here, we are looking at the SMD capacitors here. There are also two capacitors here in short circuit mode. We are checking whether they are short circuited. We are looking at the resistors that gave a signal earlier. Since the resistance of these resistors is very low, they may appear as a short circuit. Do not let that mislead you. By the way, there are two more varistors. We are measuring these in short circuit mode as well. Our varistors are back. In this case, there is no fault in the AC region, including the optocoupler. When we look at the DC region of our board, you can see there are two integrated circuits here. One is mine. This IC is a very important integrated circuit. This is the IC that provides coordination between the battery and the adapter. At the same time, we have a voltage control IC here. An IC called NC3505s. We can call this IC, in a way, the auxiliary IC for the one here. We can call it the IC that switches the voltage that needs to go to the batteries. There are two Schottky diodes. There are 1, 2, 3, 4, exactly 5 transistors and but MOSFETs. I cannot see them very clearly right now. We will perform measurements on these as well. We will do some measurements after applying voltage. We are measuring the Schottky diodes in short circuit mode. Neither of them shows any short circuit. Of course, their values are also very important. Let's look at the diode values. A diode value of 0.38. It looks normal. We are looking at the other one. Its value is quite suspicious. It looks like a problem. Anyway, we'll check it from there once we plug it into the electricity in a moment. Let's take it back to the contact section. We are also checking if our integrated circuit has a short circuit. There doesn't appear to be any short circuit. However, I am a bit suspicious of the Schottky diode. How will we measure the transistors we just counted? If we touch our negative probe to the power while in short circuit mode and get a beep when touching the other two legs, it means these transistors or MOSFETs are faulty. You can also measure them against each other in this way. So all the transistors here appear to be intact, but for some reason the voltage is passing through. After this step, we will provide 220 volts to our board to observe its behavior and try to find and repair the fault. Now let's make the 220 connection to our board. We will supply 200 volts. We must definitely not touch the SI region in particular. You can insulate this part if necessary. If you accidentally touch this part during measurement, it will cause serious problems. Air pass. What I like most is that this 220 volts hits you like God's wrath. I want to check the diode I was suspicious of earlier. We are checking the diode voltages in DC voltage mode. Interestingly, a voltage close to 8.59 volts is passing through this diode in me. Normally, yeah, you should pass between 25 and 29 volts, but for some reason it is passing 8 volts. But we are checking the other Schottky diode. No voltage is passing through this one. It might not show a short circuit, but if there's internal leakage or something similar, its value will drop and it won't pass voltage around it. But in other words, it can mislead you when measured openly or while under voltage. Let's look at the diode value. Now I'm thinking of replacing this diode and testing it, because 9 volts are passing through the board. When I examine the board, I also see that there is 5 volts here. Firstly, there is a reference voltage. I think it is 9 volts. That is what I suppose. There's a 5 minus volt DC voltage for this integrated circuit to work. What did we say about the white cable? We called it the COM cable, meaning the reference cable. By the way, I also want to briefly mention the vacuum cleaner for this adapter. This vacuum cleaner belongs to my neighbor. Now, in a moment, we will also measure the cells in this battery and see the situation together. Before moving on to the battery, let's replace the Schottky diode so as not to cause confusion and continue. Unfortunately, since I don't have an SMD Schottky diode on hand, this is a Trou Schottky diode that is equivalent to the one here. Let's unplug it from the electricity like this. I recommend you definitely do this every time after plugging our adapter into the electricity. Yes, as you can see, there was a slight clicking sound and we discharged our capacitor. So 9 volts are passing through here. We somehow need to get 5 volts and pass through so that this integrated circuit can work. As long as the integrated circuit is not working, the voltage movements here will definitely not flow through the cable. We remove the Schottky diode. I want to measure this externally as well. Let's look at it on the diode setting. It has a very low diode value. Therefore, it is not functioning. We are checking the value of the diode we will install. 0.4 for 6. Normally, this diode should have these values. There is a stripe on it. You need to find the orientation of that stripe. This stripe here needs to align with this stripe on standard diodes. When I look at it this way, our stripe was on the front side. We can order it online and replace it later. It can also work this way. It won't be a problem. We solder out diode with the stripe part facing forward. If it works, we will somehow camouflage it on the back side. I have applied the voltage. We are checking the diode that wouldn't pass voltage earlier. Once again, let's first look at the diode that we measured earlier and was passing 9 volts. The 9 volts is still there. We check the diode we installed and we see 5 volts, my friends. In this case, the problem was with this diode. So such a tiny part was preventing this adapter from working. Our 5 volts arrived thanks to the diode. Our board is working. Let's take a look at the output pins. The plus is red. The common middle pin is not showing 25 volts, my friends. A scenario comes to mind as to why it isn't coming, my friends. Actually, outboard's 9 minus volt and 5 minus volt lines are currently working. Why aren't 25 and 29 volts being output here? Why aren't they being released? This plug is connected to the vacuum cleaner. The voltage here is not released, When we look at your adapter's rating, there is 25 to 29 volts. This might confuse you. As I always say, since the system here is based on an integrated circuit, it is an intelligent system, especially with 18 and 150 batteries. Since the BMS circuit on the battery communicates continuously with the adapter, our battery starts charging at 25 volts. As the battery fills up, it uses intelligent regulation to increase the voltage to 29 volts. When it reaches 98%, it switches to 29 volts and thus completes the battery charging process So the purpose of these two voltages is exactly this. We have practically repaired our adapter. We saved the day with a single diode. For 25 volts to be output, there needs to be communication between this white wire and the BMS circuit. There's likely a problem with the battery. One or more of the cells might have failed. They might have completely lost their capacity. Let's first measure our batteries from the outside like this. From the battery that should normally give 25 volts, we are getting 2.7 volts, not even 3 volts. There's likely a very serious problem with the battery. Therefore, since our adapter isn't communicating with the battery, the 9 minus volt and 5 minus volt lines here power the integrated circuit. However, it does not send us the 25 volts because the IC understands that there is a fault in the battery. I hope all the cells inside aren't ruined and the BMS circuit isn't broken. You must be very careful. You are repairing an intelligent battery like this. If you cause any short circuit here, God forbid, you could cause the battery to explode or catch fire. When you work with these types of batteries, unfortunately, it's not really possible to extinguish them. There are exactly 6 batteries here, consisting of 18 650s and 2000 mAh. Let's measure our batteries one by one like this. When any battery here fails or loses its capacity, the BMS circuit unfortunately goes into protection mode and cuts off the voltage completely. And we're looking at the second battery. The second battery is quite normal, 3.5 volts. We look at the one right below it, 6 volts. Since it's being measured with the battery opposite it, shows 6 volts, seems to be intact. We look at the other one, 3.9 volts, 3.4 volts. All the batteries seem to be fine. Only one of them has a problem, my friends. Which one was 3.5 volts? It was this one, I think. Yes, this battery. Since we couldn't find an SMP diode, we placed a regular DF socket diode by modifying the PCB bump. Now let's briefly mention what we have done up to this point and conclude our video. We found the fault on our board. We replaced our diode. Our voltages are arriving now. Our adapter has started to release 25 volts. I also want to mention how it was left. First, let's plug it in like this. We have supplied power to our adapter. Now while it's idle, let's first measure the voltages. You see plus and minus. It's definitely not getting 24 volts. There is 9 and 5 volts on the system. We just cannot see 25 volts. To be able to see 25 volts, this plug must somehow be attached to the vacuum. There needs to be communication between this white cable and the BMS board. We are plugging in our connector. There's a problem with the battery. Unfortunately, our battery is not showing a notification light right now. You see here, our adapter is sending 25 volts to the battery. However, since there is a problem with the battery, unfortunately our battery refuses to charge. This vacuum cleaner is not mine. It is our neighbor's vacuum. I will discuss this matter with them. Our battery here needs to be replaced somehow. Since these are special batteries, I did some research online. A single battery is sold for between 300 and 500 TL. Either they will pay that money and buy a battery or replace the whole battery pack. Because when you change one battery here, since the other batteries are also worn out, any one of the batteries here might fail after a few days, a few weeks, or a few charge/discharge cycles. In that case, we would have made unnecessary expenses. If the owner of the vacuum decides to replace the batteries entirely, we will see how to remove and replace these batteries in a second video. I hope it has been a useful video. If you want to watch videos like this, you can follow our YouTube and Instagram channels. Goodbye. Take care. Goodbye until we meet again in healthy and prosperous days.